Welcome everybody to my third tutorial about testing and developing constitutive models for soils using incremental driver, which is a Gauss point element test program written by Undrained and which was further developed by us. You can find all my tutorials in GitHub, where I will provide you with the link to the YouTube account and to the tutorials in YouTube account. Until now, we did the hypoelastic umat for clay and for sand, and also we coded the linear elastic umat. And as I promised, in this third tutorial, we will deal with modified clay. In the material models library, you will see that one new constitutive model has been added, which is modified clay, which in the parameters can be called as MCC and has four different parameters. They are the compression index lambda, the swelling index kappa, the slope of the critical state line in triaxial compression, which is abbreviated by M, and the Poisson ratio, which is abbreviated by nu. There are different initial conditions which comprise the stresses, so in vertical, horizontal direction, and the three other shear components. And we have also state variables. The first state variable is the void ratio. We have in total 8 state variables. The other 6 are plastic strain components. And the last, or the 8th state variable, is the overconsolidation mean stress PC, which can be set to the same value as the mean effective pressure at the beginning, or can have a higher value, which would mean that the soil is then overconsolidated. OCR is then calculated as this PC divided by the P prime 0. The UMAT is here. You will have the source code. The UMAT was originally coded by my master thesis supervisor, which was William Fuentes, and I further modified the UMAT to fit with our needs. It is coded with an implicit integration, and we won't go into the details of the code. However, we will do different simulations. First, we will start with an oedometer test. You saw the initial conditions. So here we have an OCR of 1, a normally consolidated soil with an initial void ratio of 0.8. Then we have here the parameters as I named them before. And we have the test, where we prescribe an oedometric test with controlling the vertical stress, so S1, to amount minus 1000. So at the end, we will have 200 kilopascal plus 1000 kilopascal. In vertical direction, we'll have 1200 kilopascal. And we want to conduct 3 different oedometric tests with different overconsolidation ratios. We'll start with OCR 1. Hence, here we have PC equal to P0 prime. Now we just let it run. I have 1000 increments, 30 iterations, and 1 second, because the model is not time dependent. So let's run this simulation. It will be quick. Here we see the window. And the other one that we want to run is with OCR2. So let's name the output as OCR2. Then we have the initial conditions where we want to have OCR2. That means here 400. So 2 multiplied by 200. We run it again. And the third simulation that we want to run is the one with OCR4. That means 4 multiplied by 200. We'll have here 800 kilopascal. And in the test, we have to change the name of the output to OCR4 and run it again. Now, after we run all these 3 oedometric simulations, we want to plot them. Here I have prepared a Python file for plotting these 3 different simulations, which we see here, file 1, 2, and 3, oedometer, MCC, OCR1, 2, and 4. And you will have the source code of it in my GitHub account, and you can just also plot it by running it. And here we will see the plots. So we will see the plot for OCR equal to 1 is this one, for OCR equal to 2 and to 4. These plots are also saved here as output. This would be the newest one, would be this one, oedo.png, which I can open here. Here we will see the picture in bigger. So here we have the vertical strain versus the logarithmus of the vertical stress, and here the void ratio versus the logarithmus of the vertical stress. We see here for higher overconsolidation ratios that we first have the inclination kappa, so we have a reloading and afterwards a virgin loading. That means the normal consolidation line, and here the same for the other lines. Okay, so now we performed 3 oedometric tests to different overconsolidation ratios, and now let's continue with undrained triaxial tests. For that I will take this commando. We will put it here at the beginning. As I explained in the old tutorials, once you put here an end, then incremental driver won't read further, so it will end here. So we have here a CU test with the MCC model for OCR equal to 1. Then for OCR equal to 1, we have to put here 200. And what I'm running is 30% of deviatoric strain. Now we can run it for OCR 1. It's very fast, so it is already done. Then OCR 2. For OCR 2, I made now a mistake. We have to change initial conditions to make here 400. And I will run it again. These simulations are really fast. And then we need the last one for OCR 4. That means a pre-consolidation pressure of 800 kilopascal. And here to change the output, which will be OCR 4. So we perform the same test, but only with different OCRs, so initial conditions. Then we want to plot it. Again, you will have the source code for all these 3 files that we just produced in my GitHub account. And here you see the lines. So you see OCR 1, the blue, OCR 2, red, and OCR 4 in green. Here you see, as we know, in the effective stress path, we see the blue one, which is only with prevented contraction. So we have increase of the mean, an increase of the excess pore water pressure. That means a relaxation of the mean effective pressure. However, for an OCR2 for modified CAM clay, then we know that it will be only a vertical line here until reaching the critical state line, which is here denoted with a red dotted line, is the critical state line. And for a heavily overconsolidated soil, then we will reach a peak state and afterwards approach the critical state line by following the yield surface. That was for an undrained triaxial test, and the next one would be a drained triaxial test. So I have all commandos saved here. Then I will just take the CD, consolidated drained triaxial test, first with OCR equal to 1. That means here 200 again. Then with OCR equal to 2, as previously. So always 1, 2, and 4. 2. And the last one with OCR equal to 4. And initial conditions here 800. Yeah, so now we can plot also the drained triaxial tests. The code for plotting them is here. It will be provided in the GitHub account in the session 3 of the tutorials, and it is named then triaxial, so triax underline CD, consolidated drained. And if we plot them, then we will see in Q epsilon 1 space OCR 1, 2, and 4. And in volumetric versus vertical strain, we will see that we have for OCR 1 only contraction. For OCR 2, we have a slight decreased contraction. And for OCR 4, we have, after an initial contraction, dilatant behavior. For OCR 8, this dilatant behavior would be even greater. So we see the course of the curves as we would expect from a modified CAM clay. A next test and the last test that I would like to perform today is a cyclic undrained triaxial test, which I didn't perform until now. So in the tutorials, this would be a new test that we are performing here. And with that, you will be learning a new commando here. As we see here, okay, the first we have the name of the output, so it would be CU test, cyclic, with an amplitude of 90 kilopascal here. Then we have triaxial UQ. So the difference between this undrained test and the first undrained test that we performed today is that here we had UEQ. So here we were controlling the deviatoric strain. However, here we are controlling the deviatoric stress. So we have only Q, not EQ. And with that, we control here the deviatoric stress of 90 kilopascal. So these commandos are all in the manual of incremental driver that you have also online in my GitHub account. Then the next commando is something new today, which is repetition to 10. That means repeat the next two steps, which means this step and these steps, 10 times. So repeat these two steps 10 times. That means that we will be performing a cyclic triaxial test by repeating the next ones for 10 times. That means we are performing 10 cycles. Let's now run this simulation, and I would like to run another one with a higher amplitude. So this is still simulating here. And after this is done, then, okay, here we had a highly overconsolidated soil, so we won't see any plasticity. So let's make it for OCR1, that means PC equal to 200, and run the simulation in order to see any plasticity. So here the simulation is running, and then the next one would be for 100 kilopascal, and here 200, here also 200, and to change the output file to 100 because we have another amplitude. Now we will run this one because the other one was finished, and then we will plot them here with this file where we have these two Q90 and Q100, and we will plot the simulation. So always, if we want to repeat one step or two steps, then we can use this repetition, and then it will repeat the next n steps for 8 times. Then let's plot the simulation. So as we see it here, we are performing a cyclic triaxial test, undrained. And we can even plot it in the negative. That would mean from minus 120, for example. And here also minus 120 to really see the cycles. Yeah. Now we see here that we are performing, first, we are loading the sample with 90 kilopascal, that we are unloading it with minus 180 kilopascal. So to come to the same stress here in extension. And then again, we are doing the same. This is in effective stress space, and in Q versus epsilon 1 space, that would be loading until 90 kilopascal, then unloading, reloading, unloading, reloading. However, as modified CAM-clay model is a elastoplastic model, we see here that after reaching the yield surface and unloading and reloading, we remain inside it, and we don't produce any plasticity if we don't increase the load, so the amplitude. We have here also the comparison with another amplitude, which is 100 kilopascal, and we see that we produce some more plasticity during the first loading. However, after unloading and reloading, we do not produce any more plasticity because the yield surface has been expanded to this value, and it can produce only plasticity if we try to load the sample to a higher stress than this. So let's reassemble what we have done today from simulations. So we were testing the modified CAM-clay model with incremental driver. You will see the umat in my GitHub account and the tests that we were performing today, the initial conditions and the parameters. And the material models library has been extended for modified CAM-clay. We performed different tests. First, we performed 3 oedometric tests with 3 different overconsolidation ratios to see the slope of the reloading line and the slope of the normal compression line, so kappa and lambda. Then we performed 3 undrained triaxial tests with different OCR values. Here you don't see the red line because it's behind the green line, and it goes from 200 vertically to the critical state line, and it ends there. You see it also here that it reaches the same value. And what we also know here is that the yield surface of modified CAM clay will intersect the critical state line at PC divided by 2, which means here, or at PC divided by 2 here, because we had an overconsolidation ratio. Then the next test that we performed were 3 drained triaxial tests with different overconsolidation ratios by changing from contractant behavior to dilatant behavior. And the last but not least test was the undrained cyclic triaxial test with 2 different amplitudes of 90 and 100 kilopascal, where we again saw that after reaching the maximum loading, when we do an unloading and reloading, a cyclic test, then we won't produce any plasticity anymore, which means that the excess pore water pressure won't accumulate anymore, and we won't relaxate in the effective mean pressure. I thank you very much for your attention and for your interest in my tutorials. I am very happy to be able to share these things with you and to raise the awareness of advanced constitutive modeling in geotechnical engineering, because I really think that we need this in future, especially with the new demands on different cases that we have to deal with in geotechnical engineering. And in the next session, I will be going on with other material models for clays with time dependency. Thank you. Goodbye.